All right. So again, I think that you really do need to think about this a little bit. So whenever they say decreased temperature, don't just sit there and say, well, if this was increased temperature, these arrows are opposite. Sit there and talk yourself through it, because the more you talk yourself through it, the better understanding you're going to get. So if we take a look, we're decreasing temperature. So that basically means we're taking out heat. Since heat is a product, we're taking out products the system wants to make. Then to reach that ratio that we've established, that K to BQ, the system needs to make more product. And keep it in mind, as it makes more heat, it's going to end up making these two. So their concentration will go up. And what does it use to make these things and heat? It uses the reactants. So their concentration will go down. Again, pressure is a weird thing. You've got to look at moles. We have 4 and 5, so that's 9. We have 4 and 6, that's 10. So at STP, which of these takes up more space? Well, the products would take up more space, because any 1 mole at STP takes up 22.4 liters of space. The product will take up more space. If we increase pressure, that puts a squeeze on it. So that squeeze then wants to basically be the smallest number of moles. If it's getting squeezed, that means this side is the smallest number of moles. So we will increase making those and decrease making this. So if we increase making this, we have to use up products here. Decreased pressure is the opposite. So if we think about it, we can expand. If you've ever been in a crowded elevator, or at the at the front of the concert or whatever, and all of a sudden people start leaving, you got all that room, you can start to dance, and you can start to spread out a little bit in the elevator. So that's what's going to happen. We're going to allow more moles here. So those will increase, and if we have more moles of product, we got to use up some of this reactant. We're going to have less moles of that. Adding a catalyst. Adding a catalyst will speed up forward and reverse reactions and will do nothing. Cool. Hopefully we're all right with that. Again, there's many more pages on this. I will try to put up the answers for these. This one's different than what we talked about. Adding a small amount of a helium gas. So if we take a look, we have 2 moles of ozone, and that yields 3 moles of O2. So we have 2 moles on one side, 3 moles on another. Adding a small amount of helium gas. It's a special case. Initially, we think by adding helium gas that's going to increase the pressure. But as long as we don't have a change in volume, if we're looking at concentrations, these concentrations will still be the same. We still have the same number of moles of each of these gases at the same volume. Adding the helium gas, since it doesn't react, these guys will be colliding and bumping with helium gas just as much as these guys. So there won't be any change here. So it's kind of a big one right there. We know helium is inert. Basically, that means it doesn't react with things because it's a noble gas. Whenever you pump that in, it's not going, if you don't have a change in volume for this, if it just says, okay, we pump in some helium gas, the actual concentrations are still the same because we still have the same number of moles of each of these. We haven't changed the volume, so moles per liter is equal. It's the same as it was before. So adding that won't affect it because, I mean, they're going to collide with each other just as much. Like this will collide with each of these equally if you pump that in there. Changing the shape of the container without altering the volume. Again, we're not altering the volume, so that's not going to have an effect. Increasing the volume, what does that do? Concentration. Easiest way to say it is changes it. And that's all you need with this. It changes the concentration. Increasing the volume changes the concentration. What can the system do to reach back to equilibrium? Well, increasing the volume allows for more space. This O2 takes up more space. That would be favored. You can say shift right. You can say more product formed, or you can say that the forward reaction is favored. So just along the lines of adding an inert gas, we have add to the content a fourth chemical that reacts with nitrogen. Down here, fourth chemical where something reacts with nitrogen, what that's going to do is that's going to lower the concentration of nitrogen because it will be reacting and forming something new. If we lower the concentration of nitrogen, system says we need more nitrogen to reach equilibrium. So what makes more nitrogen? That would be the shift left or the reverse reaction being favored. This is interesting too, because if we look, that's solid. So adding more solid I2 would have no effect. Removing all the solid iodine, this is actually a big one. And I can't imagine anybody asking you this. That's probably why it's on this sheet, is just to sit there and have you think. But removing all of the solid iodine, that means we have none of this. If we remove it all, some will have to form, right? Some will have to form. If we're at equilibrium and we remove all this, some will have to form. It may be very little, but at least a small amount will have to form. You may not even be able to see it. As long as it's there, it's good though. It's in the reaction. Keep in mind, since we have that solid iodine, excuse me, we have 1 mole of nitrogen and 1 mole of dinitrogen tetraiodide. The number of moles on each side of this are equal. So if we change pressure or volume with these two, there will be no change. So increase in volume, no change. Add a small amount of neon gas. Well, as we talked about up here, we're not changing the volume of the system. So that won't be any change anyway. Another way to look at this is they do tell you that it is positive 55 kilojoules for the delta H. That means it's endothermic. So which side are we writing heat on? Anybody? Plus 55 kilojoules delta H. See, go on the product side or reactant side?
Product. No, sorry, reactants.
All right, yep, you just made it just in time. If you would have let that hang for another second, I would have thought you didn't know what you're talking about. But when you switch it that quick, yep, it's going to be on the reactants. We are gaining energy, so heat is going to be here, right? Mr. Jackson with extra money is a positive thing. So we're gaining the heat there. Questions about Le Chatelier's? Again, I'll try to get the answers up there tonight for this. Page 14 is the quotient thing. Basically, they're saying, okay, this is the equilibrium constant. Plug this into the equilibrium equation and tell us whether or not it's at equilibrium where nothing is favored. If the Q is greater than equilibrium, we're going in the reverse fashion. If Q is less than the equilibrium, then we're going in the forward fashion. Let's do one of these. I think, hopefully, I feel like this is pretty common. I think it makes sense mathematically. All right, so if we take a look at this, we're going to put nitrogen and hydrogen on top. Hydrogen is cubed. Remember, these are almost like rate laws with the elementary reaction. We're going to put reactants on bottom. So that equals K sub BQ, which in reality equals Q. They're found the same way because Q is K sub BQ, but K sub BQ is at equilibrium. Q may not necessarily be at equilibrium. And that's what we're trying to figure out with this. So I think we can just punch these into the calculator. Make sure everything, I want to make sure everything's not solid or liquid. I want to make sure everything's either aqueous or gas for that. So then we will clear. And we will put into 1 times 1. I did pick the easiest one ever, right? 1 times 1 cubed divided by V1. Yes, not good. 0.2 square. So we get 25 for that. So Q equals 25. 25, Q is greater than 17. So keep in mind again what this actually means. This is a ratio of products to reactants. So the equilibrium constant says it should be 17 to 1. We are currently at 25 to 1. We need to get less products to reactants. How do we get less products to reactants? We take some of the products and we turn them into reactants. So we favor the reverse reaction. And again, the rest of this is exactly the same. Basically, it's making sure that you can cube things and square things and all of that. And that you pay attention to that. Are any of these actually trying to trick you with solids and stuff? Man, they didn't. I don't see when it does. Why does 5 look so ridiculous? Just because it's a long equation. And then the at 6, what's favored at equilibrium? Products or reactants? So K has 1 times 10 to the negative 13. Is that a big number or a small number? Very small. So that means that we are favoring the reactants. The bigger the K, the more we favor the products, right? All right, so if we take a look at this, again, I'm sorry that I did not have time, but to tell you the truth, I mean, since we went virtual at this time last year, you may not have, this may not have made it into your teacher's wheel well or whatever. If we take a look, this is a solubility product constant. This is Ksp. Whatever you're starting with is solid all the time. So that's the reactant. So if we look at the same thing we have, and this works with physical versus chemical reactions as well. That's the beauty of it, this equilibrium concept. We have 1 on the bottom of all of these. So basically we take K sub EQ to change it to the solubility product constant. We have 1 at the bottom. And basically then we look at this and we write out the actual, the products. So on the surface, that's indium, right? Indium. This would be the concentration of indium. We would take it to the 2nd power, and then we would multiply it by sulfur, and we would take it to the 3rd power. So if we take a look at aluminum phosphate, we would have the aluminum. Since it's a 1, we would have 1 phosphate. it would also have 1. Now, that's probably the simplest thing you've seen in a while. But here's the issue with this. And I'm trying to think of a way to ask this question so that I can get a little insight how hard or how easy this is, because you guys always tell me exactly what I need to know when it comes to your understanding. I just want to make sure that we're on the same page on that. So, but if we have 1 mole of indium sulfide, the concentration of indium here is what? So if I make this X, this is, or let's just make it 1 mole. Let's go ahead and give you the actual 1 mole of this. How many moles concentration-wise of indium do I have?
2.
2. And how many moles of sulfur, in this case, the sulfide ion, do I have?
3.
3. So that's the thing. If we look at this as being 1 and this is out of the picture, in reality, the concentration of this, if I know the concentration of this, the concentration of this is actually doubled. And the concentration of this is actually tripled. Because for every 1 of these I get, I have 2 of these and 3 of these. I don't, again, I mean, I don't know how much sense that makes to you, but let's take a look down here. We have lead chloride, right? So we have PbCl2 breaking down into 1 Pb lead ion, lead 2 ion, and 2 chloride ions. So if we take a look, K sub EQ equals products over reactants. K sub SP equals, well, we don't have reactants here because it's solid. So we would just change that to 1. We have the concentration of the lead 2, right? And we have the concentration of the Cl negative. And the Cl negative is squared, right? But if we look at this concentration here and this concentration here, if we dissolve this, the concentration of this should be twice as much as the concentration of the lead. Because for every 1 lead we get 2 moles of Cl negative. That makes sense. Good, I'm glad. So if we take a look here, if we're trying to solve for X for this, basically we're trying to solve for the molarity that whoever put in there. This is the solubility product constant. Let me ask you this, is this very soluble or slightly soluble? Sounds like a crazy question, but all you got to do is look at the KSP. Think of it as the equilibrium product of the equilibrium constant. Is the KSP less than 1, greater than 1? How much so? If it's greater than 1, this is very soluble. If it's less than 1, it's not very soluble, right? So what is this number? 1.7 times 10 to the negative 5th. How's it compare to 1? Not very soluble, right? So these questions that, I mean, like they sound like, wait, what am I doing? But all you've got to do is think about what we've talked about. If it is much greater than 1, then that means that a lot of this stuff's made. If it's not greater than 1, then a lot of this stuff is occurring. So in this, if you dump that into water, you would probably see, depending on the quantity of water and the quantity of it you use, you probably see this sitting at the bottom, right? Just keep that in mind. That's all that KSP means, is how well it dissolves. Which is kind of cool to think that somebody actually has a number to sit there and say, that's how well that dissolves. Not very well. I mean, in reality, I mean, that's all that number really means to us on the surface. But it will also tell us how many moles dissolve in there, which then we could use for stoichiometry. Yay. Right? Woohoo! So if we take a look, The thing about this is we have KSP. They want X in the molarity of what we put in there or what is actually dissolved from there. So if this is the KSP, we know this number. The problem is that for every one of these is made. And for every one of these, two of these are made. So basically what we have to do is if we're going to put these in there, this becomes X and this becomes anybody. You know, math is my worst subject, guys. Come on. If this is X, how many of these are made? So that will be 2X, right? Good. And we will have to also square it. Yeah. Because it's still the old, whatever the coefficient is becomes the power. The old coefficient becomes the power with these because of looking at it like an elementary reaction or whatever. But the key thing here is if this is X, this is 2X.
So when you have a coefficient, it goes in front and it's the power, like it stays a coefficient and it becomes a power.
I really don't like the way you're saying that because I think that's I think you're trying to oversimplify it. Do you like? We should all understand that basically this means the concentration, right? That's what the brackets are for. And we know that in an elementary rate law reaction, the coefficient is the power. But when we're looking at this, whatever the concentration of this PB is, the concentration of the Cl will be twice as much. So whenever you just say, oh, so the 2 goes like twice, I think that and I hate thinking, but I think that I don't think that you can actually sit there and simplify it that much. I think you actually have to think about this is say, okay, for every 1 mole of this, there's 2 moles of this, and that's why the concentration of this will be doubled. The square, I think, is totally independent of that. It is based on that, but it's based on like there's a lot more to it than just saying this is twice the amount of this. That square, I think refers to more of like it's bigger than that. I guess is the only way I can say it. But if that helps you, sure, by all means, think about it like that. But I wouldn't try to make a simplification on this. I would try to think it through. That way you don't get caught on something silly.
So is it possible for like something to have a square but not have a coefficient of 2 in front of it?
No. So I mean, but I think that you should think about it a little bit more. I think you should think about it like it's a 1-to-2 ratio here. The square mathematically is important, yes, but like I think about it however you want. I guess. I mean, yeah, if that makes it easier for you, then sure. Do it your way, Hayden. You got this. Like I said, maybe it's my lack of math skills that makes me nervous about thinking about it that way. So yeah, you're probably good then. But anyway, so what does this become? 2 squared x squared, right?
4x squared.
Good. And then we're going to multiply that by x. So that becomes 4x cubed. And then we know that that is equal to 1.7 times 10 to the negative 5th. First step for solving this, we're going to divide both sides by 4 and then take the cube root of it. We should be able to do all of that in our calculator. So 1.7 times 10 to the negative 5th divided by 4 cube root. Oh, I did something wrong. I don't know how to work these. How do you do cube root? Somebody, do I just take it to the negative 1/3 or whatever? Anyone? Anyone?
I think you could just take it to the 1/3, but there might be a way on those calculators. I'm not
Oh,
sure.
there we go. It's right here. So if I take a look, I don't know how to do this. 3, and then this, and then answer. Does that make sense? So it's saying that the x up there is the 3, so that's a cube root, and then the answer I just got. I get 1.6 times 10 to the negative second. 1, 2, 4, 0.016. 2 significant digits. I think we're good. Questions there? And again, I mean, like, you guys may have been like, this is easy, but keep in mind, you've got to check this. Keep in mind why the bottom of this is 1 and why we do need to take the 2x there if we square it. And if Hayden's thing makes you like, if we're squaring this, then multiply the concentration by 2. If that helps you, by all means. But I think it's better. I do think it's better. I don't know why. But I think it's better if you sit there and look at this as like, for every one of these we're going to make 2 of these. And then looking at this like, you know, an elementary rate law, we know we square the concentration of that. And then obviously this will be double the whatever the concentration of the PV is. That's all I got for today. Again, I will try to put the answers up to everything up to page 15. Any questions?
Nope.
All right. Again, I will not be available tomorrow. If you guys are coming in tomorrow, see if you can't come a little bit later. Otherwise, you'll be sitting here with I don't know what and just sitting here. The assignment for tomorrow, as you guys know, is to catch up working through these problems, page 1 through 15. Other than that, have a great weekend. Have a great day. Gain your energy. Gain your energy. Bye.
Thank you.
Lily and Diego, are you guys ever coming back in?
I didn't because I didn't see the point.
What's that?
I didn't this time because I didn't see the point.
Me either. I don't see the point either. But that means we didn't know that, you know, that was the last time we might ever see each other. That's kind of sad, right? I mean, you guys get to see me, but you guys never turn your camera on, so I was always have to. You know I'm teasing. Have a great week, guys. You guys.
Thank you. You too.
You too.
Thank you.
What'd you ask? Sorry.
I asked you if you had any plans for this weekend.
Oh, my internet was going out.
Oh no. Lily's catalytic converter got stolen, so I gotta. Yeah, I'm trying to replace it myself.
Good luck.
So,
yeah, they
yeah.
My oxygen lines too.
Your what?
The oxygen sensors. So I have to get new oxygen sensors as well.
Catalytic converter has that platinum and rhodium in there. That's quite expensive metals.
Yeah, I think I might remember you talking about that in chemistry.
Yeah, right? Like, I can't believe they took that. Oh, it sucks.
Yeah.
See you later. Thank you. Well, good luck with
Thank
it.
you.
Hopefully it's not too hard. I mean, if somebody can rip it off of there, you should probably be able to put it back on without too much trouble.
Yeah, I think so.
Have a good weekend.
Right.
You guys too.
Thank you.
Take care. Bye. Good morning, man. How are you? Doing all right. Tired? Me too. That's about the time I got up. That's